In January 2026, NASA confirmed the most distant galaxy ever detected. A galaxy that exists just 280 million years after the Big Bang. Brighter, more complex, and more chemically enriched than any model predicted. The scientist who found it said it looks nothing like what we expected. That same year, the biggest crisis in modern cosmology crossed the threshold physicists use to declare a discovery. Two ways of measuring how fast the universe is expanding give two different answers. And the gap is no longer a tension. It is a crisis. Our model of the universe may be broken. And if it is broken, then everything we thought we knew about how big the cosmos actually is, how it formed, and what it is made of, comes into question. Tonight, we are going to travel from the surface of this tiny planet to the edge of everything light has ever reached. We are going to discover that 80% of the universe is empty. That 95% of everything that exists is made of something we have never detected and do not understand. We are going to stand inside a void 330 million light-years wide that contains almost nothing. We are going to see the first photograph ever taken of the cosmic web, the largest structure in existence. And we are going to confront the possibility that the observable universe, all 93 billion light-years of it, may be a keyhole, and the room behind it could be 100 sextillion times larger. By the end, you will understand why the question, "Are we alone?" may not be about biology at all. It may be about architecture. The universe may be built to keep us apart. If you enjoy our nighttime science journeys, remember to like and subscribe. We highly encourage our community to discuss the video topics in the comments and react to other comments. It is the most fun when we share our thoughts. And if you struggle with memory or just want to improve it, try our affiliated partner, The Brain Song, a daily 12-minute audio routine backed by neuroscience that helps improve your brain memory capabilities. You can read more in the video description. Now, let us begin. Tonight, we are going somewhere that will make you feel very, very small. Not small like standing at the base of a mountain. Not small like watching a storm roll across a flat horizon. Small in a way the human mind was never designed to process. Because tonight, we are going to measure the universe. And what we are going to find is that almost everything you think you know about how big it is, how it works, and what it is made of is either incomplete or flat out wrong. Over the next 2 hours, we will travel from the surface of our tiny planet to the edge of everything that light has ever been able to reach. We will discover that 80% of the universe is empty. That 95% of everything that exists is made of something we have never directly detected and do not understand. We will learn that the largest structure in the known universe was photographed for the first time just last year. A strand of gas and dark matter stretching 3 million light-years between two ancient galaxies. We will confront the biggest crisis in modern cosmology. A disagreement about the most basic property of the universe, how fast it is expanding, that has now reached the threshold physicists use to declare a discovery. And we will meet a galaxy that should not exist. A galaxy that appeared just 280 million years after the Big Bang, brighter and more complex than any model predicted. A galaxy that the scientist who found it said looks nothing like what we expected. And at the very end, we will ask the oldest question there is, are we alone? But by the time we get there, you will understand that question differently than you ever have before. Because the answer may not be about biology, it may be about architecture. The universe may not just be too big for us to find anyone else. It may be built to keep us apart. Chapter 1. The universe is lying to you. Go outside tonight. Find a dark spot away from the streetlights if you can. Look up. Let your eyes adjust. After a few minutes, you will see thousands of stars scattered across the sky. On a truly dark night, far from any city, you might see as many as 4,000. It feels infinite. It feels like you are looking at the universe itself, spread out above you in all its grandeur. You are not. Almost every star you can see with your naked eye is within about 1,000 light-years of Earth. That sounds like a lot. 1,000 light-years. But the Milky Way galaxy is 100,000 light-years across. That means you are seeing roughly 1% of the diameter of your own galaxy, and that 1% contains almost nothing compared to what lies beyond it. The Milky Way holds an estimated 250 billion stars. You can see 4,000 of them. That is like standing in New York City and being able to see one building and calling it the skyline. Now consider this. The Milky Way is one galaxy. The observable universe contains an estimated 2 trillion galaxies. Each one holds billions or hundreds of billions of stars. The total number of stars in the observable universe is estimated at 10 to the power of 24. That is a 1 followed by 24 zeros. It is more stars than all the grains of sand on every beach on Earth. And every single thing you have ever seen when you looked up at the night sky is a microscopic sliver of one of those 2 trillion galaxies. The night sky is not a window into the cosmos. It is a peephole, and what you see through it is your neighborhood. The universe is vastly, incomprehensibly larger than anything the night sky suggests. And here is the unsettling part. Even the scientists who study it for a living are now discovering that their own picture of the cosmos might be fundamentally wrong. There is a number in cosmology called the Hubble constant. It measures how fast the universe is expanding. It is one of the most important numbers in all of physics because it tells us the age of the universe, the size of the universe, and the fate of the universe. Get this number right, and the rest of cosmology falls into place. Get it wrong and everything unravels. For decades, scientists had 2 ways of measuring the Hubble constant. The first method looks at the cosmic microwave background, the leftover radiation from when the universe was just 380,000 years old. Using data from the European Space Agency Planck satellite, cosmologists mapped this ancient light and used the standard model of cosmology, known as lambda CDM, to calculate the expansion rate. They got a value of about 67.5 kilometers per second per megaparsec. The second method uses what is called the cosmic distance ladder. Astronomers measure the distances to nearby stars, then use those measurements to calculate the distances to more distant galaxies, and from that, they calculate how fast the universe is expanding locally, right now. This method gives a value of about 73 to 76 kilometers per second per megaparsec. The difference between 67 and 73 might not sound like much, but in precision cosmology, it is enormous. And, by late 2025, this discrepancy had reached what physicists call 5 sigma. That is the statistical threshold used to declare a discovery in physics. The same threshold that was used to confirm the existence of the Higgs boson. This is no longer a minor disagreement. Daniel Skolnick, a physicist at Duke University, put it bluntly. He said, "We have been at this Hubble tension level for a long time, and at some point the community needs to say this is more serious." In 2024 and 2025, the James Webb Space Telescope was used to re-observe the same Cepheid variable stars that had been used for the local measurements. The goal was to check whether dust or instrument error had contaminated the data. The result: the original data was correct. The local measurement of about 73 kilometers per second per megaparsec is robust. Then, in December 2025, the TD Cosmo collaboration published an entirely independent measurement using gravitational lensing, watching how light from distant quasars bends around galaxies. Their result matched the local value. Every new technique that measures the expansion rate of the local universe gets the same answer. And it is the wrong answer, according to our best model. The standard model of cosmology has survived every test for 25 years. It may now be cracking, and the cracks do not stop at the expansion rate. In January 2026, NASA announced the confirmation of the most distant galaxy ever detected. It is called MOM-Z14, and it sits at a redshift of 14.44. That means its light has been traveling through expanding space for over 13.5 billion years. We are seeing this galaxy as it appeared just 280 million years after the Big Bang, when the universe was just 2% of its current age, and it should not be there. MOM-Z14 is brighter, more compact, and more chemically enriched than any model predicted for a galaxy at that age. It contains elevated levels of nitrogen, an element that normally requires multiple generations of stars to produce. But 280 million years is not enough time for that. The galaxy has even cleared its surrounding region of primordial hydrogen, something astronomers did not think was possible at that epoch. Rohan Naidu of the Massachusetts Institute of Technology, the lead author of the study, said with Webb, "We are able to see farther than humans ever have before, and it looks nothing like what we predicted." And MOM-Z14 is not alone. The James Webb Space Telescope has found over 100 bright galaxies at redshifts above 10, in an era where pre-launch models predicted essentially none. The number density of bright galaxies at this distance is more than 100 times larger than the consensus models expected. Among them is Zhulong, a Milky Way-sized spiral galaxy discovered at a redshift of 5.2, just 1 billion years after the Big Bang, already possessing a mature central bulge, spiral arms, and 100 billion solar masses. A galaxy that looks like it has had billions of years to evolve. It had a few 100 million. Jacob Shen, a postdoctoral researcher at MIT and a member of the MOM-Z14 research team, said there is a growing chasm between theory and observation related to the early universe. The Big Bang itself is not in question. The cosmic microwave background, the abundance of light elements, the ongoing expansion of space, all of these confirm that the universe began in a hot, dense state roughly 13.8 billion years ago. What is in question is the timeline. Galaxies are forming too fast, too bright, and too structured for the standard lambda CDM model to explain. Something is missing from our understanding, something fundamental. And if our model of the universe is breaking, what else are we getting wrong? How much of reality have we never even seen? To begin to answer that, we need to start with what we know. We need to start close to home and work our way outward. And close to home, the first lesson is humbling, because even the distances within our own solar system are enough to make you realize that the universe was not built for us. Chapter 2. You are here and you are nothing. Let us start with the closest thing to us, the moon. It hangs in the sky, looking almost close enough to touch. Poets write about it as a companion, a neighbor, a fellow traveler through the dark. But the moon is not close. It is 384,400 kilometers away. That is far enough to fit 30 Earths lined up side by side between us and it. A rocket traveling at escape velocity takes about 3 days to get there. A Formula One car at top speed would need 42 days. And this is the closest celestial body to Earth. This is the first step on the staircase, and it already takes 3 days at 28,000 kilometers per hour. Now take the next step. Mars, the red planet that dominates our imagination when we talk about becoming a multiplanetary species. Mars, at its closest approach, is about 55 million kilometers away. At its farthest, it is over 400 million kilometers. The average distance is roughly 225 million kilometers. That is 585 times farther than the moon. A signal traveling at the speed of light, the fastest speed possible in this universe, takes between 3 and 21 minutes to travel one way between Earth and Mars. When NASA sends a command to the Curiosity rover, they wait up to 21 minutes just to hear if the command was received. Conversations are impossible. Real-time communication is impossible. Mars is right next door, and it is already beyond the reach of a phone call. In 2014, the Curiosity rover turned its cameras upward and photographed the Earth from the surface of Mars. In that image, our entire planet is a faint bluish dot in the Martian sky. Not a marble, not a jewel, a dot, barely distinguishable from the surrounding stars. Everything you have ever known, every person you have ever loved, every city you have ever visited, every war ever fought, every song ever written, reduced to a smudge of light in someone else's sky, and that is just from Mars, our nearest neighboring planet. Now, let us leave the solar system, or rather, let us try, because leaving the solar system turns out to be almost unimaginably difficult. The farthest human-made object in existence is Voyager 1. It was launched in 1977. It has been traveling continuously for over 47 years, at a speed of roughly 61,200 kilometers per hour. As of now, it is approximately 24.6 billion kilometers from Earth. That sounds impressive. It is. No human creation has ever traveled farther. But Voyager 1 has not left the solar system, is less than #0. 5 hash is greater than. The solar system is much larger than most people realize. Beyond the planets, beyond the Kuiper belt where Pluto orbits, there is a vast shell of icy debris called the Oort cloud. It extends from roughly 2,000 astronomical units to perhaps 100,000 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, about 150 million kilometers. Voyager 1 is currently at about 165 astronomical units. It will not reach the inner edge of the Oort cloud for another 300 years, and it will not pass through to the other side for roughly 30,000 years. 30,000 years. That is longer than all of recorded human history, longer than the entire span from the cave paintings at Lascaux to this moment. And at the end of those 30,000 years, Voyager will have merely exited our Sun's stellar neighborhood. It will not have come close to another star. The nearest star to our Sun, Proxima Centauri, is 4.24 light-years away. At Voyager 1 current speed, it would take over 73,000 years to reach it. If Voyager 1 had launched at the dawn of modern human civilization, when the first cities were being built in Mesopotamia, it still would not be there yet. Strapped to the side of Voyager 1 is a golden phonograph record, the Voyager Golden Record. It contains 48 images encoded as audio signals, greetings in 55 languages, 27 pieces of music, from Bach to Chuck Berry to Javanese gamelan, sounds of earth, thunder, wind, birdsong, a mother kissing her child. It was designed by a committee chaired by Carl Sagan. The record is a message in a bottle thrown into a cosmic ocean. It was meant to communicate who we are, what we sound like, what we value, to anyone who might find it. The odds of anyone finding it are essentially 0. Space is too vast. The distances are too great. Voyager 1 will drift through interstellar space for millions, perhaps billions of years. The record will outlast every building, every city, every civilization on Earth. It will outlast the Sun itself, and in all likelihood, no one will ever play it. It is the loneliest artifact in existence, a love letter addressed to no one, floating through the dark. But perhaps the most sobering measure of our insignificance is not how far Voyager has traveled. It is how far our voice has carried. Since the early 20th century, humanity has been leaking radio and television signals into space. These electromagnetic waves travel at the speed of light. They are the fastest thing we have ever produced. And they have been spreading outward from Earth for roughly 125 years, creating an expanding sphere of human noise 125 light-years in radius. That sounds like a respectable distance. It is not. The Milky Way galaxy is 100,000 light-years across. It contains an estimated 250 billion stars. Our radio bubble, 125 light-years in radius, encompasses roughly a few thousand of those stars. If you placed our radiosphere inside a map of the Milky Way, it would be invisible, a microscopic dot, a grain of sand on a beach. Beyond 125 light-years from Earth, no civilization has ever had the opportunity to hear us. No signal has reached them. No evidence of our existence has arrived. We are, cosmically, silent. We have been shouting into the void for a century, and the void has not noticed. And here is the thing that should keep you up at night. The Milky Way, this enormous spiral galaxy that dwarfs everything we have ever known, is itself just one galaxy. One galaxy among 2 trillion in the observable universe. And until 1920, we did not even know that other galaxies existed. In 1920, the astronomical community held what became known as the Great Debate. On one side was Harlow Shapley, who argued that the Milky Way was the entire universe. All those fuzzy patches of light seen through telescopes, the so-called spiral nebulae, were just gas clouds within our galaxy. On the other side was Heber Curtis, who argued that at least some of those nebulae were actually separate galaxies, island universes far beyond the Milky Way. The debate was settled in 1924 when Edwin Hubble, using the 100-inch telescope at Mount Wilson Observatory, identified Cepheid variable stars in the Andromeda Nebula. These stars pulsate at rates that correspond to their intrinsic brightness, which allows astronomers to calculate their distance. Hubble measured the distance to Andromeda and found it was approximately 900,000 light-years away, far too distant to be inside the Milky Way. Andromeda was a separate galaxy. Later measurements revised the distance to about 2.5 million light-years. In one observation, the universe became unimaginably larger. What had been the whole of existence, the Milky Way, was suddenly just one island in an ocean of galaxies stretching in every direction to the limit of what telescopes could see. And that ocean, we would soon discover, is not a calm or uniform place. It has structure, it has patterns, it has vast regions of terrifying emptiness. Emptiness so complete that if you stood inside it, you would not know the rest of the universe existed. The universe is not just big, it is mostly nothing, and what is there has organized itself into a pattern so vast and so strange that we are only now, in the first decades of the 21st century, beginning to see it clearly. That pattern begins with the voids, the great dark spaces between the stars, the enormous regions where the lights go out and nothing, almost nothing, remains. Chapter 3. The Great Nothing. In 1981, an astronomer named Robert Kirshner at the University of Michigan was conducting a redshift survey. His team was mapping the positions of galaxies in 3-dimensional space, measuring not just where they appeared in the sky but how far away they were. It was routine work. Galaxy surveys had been done before. But when Kirshner team plotted their data in a region near the constellation Bootes, they found something unexpected. A gap. A massive, spherical gap in the distribution of galaxies. They checked their instruments. They rechecked their data. The gap was real. They had discovered the Bootes void. The Bootes void is a roughly spherical region of space, approximately 330 million light-years across. To appreciate that number, consider that the entire Milky Way galaxy is 100,000 light-years in diameter. You could line up more than 3,000 Milky Way galaxies across the width of the Bootes void. It is one of the largest known voids in the observable universe, and it is almost empty. In a region of that size, astronomers would expect to find roughly 2,000 galaxies. The Bootes void contains approximately 60 galaxies in a volume that could hold thousands. Those 60 galaxies are clustered along a thin tube-shaped region running through the middle of the void, like a handful of crumbs scattered along a thread in an otherwise bare room. The rest is darkness. Nothing. An ocean of space with no islands. The astronomer Greg Aldering once offered a thought experiment that captures the loneliness of the Boots void better than any number can. He said that if the Milky Way had been located at the center of the Boots void, we would not have discovered that other galaxies existed until the 1960s. Think about that. We would have looked out into the sky with the best telescopes of the 19th and early 20th century and seen nothing. No Andromeda, no Magellanic Clouds, no spiral nebulae to debate. We would have believed we were alone, the only galaxy in an infinite black sea. And we would have been wrong, but we would have had no way to know it. The Boots void is not an anomaly. It is one example of a feature that dominates the universe. Voids. Enormous, roughly spherical regions of below-average galaxy density that together make up approximately 80% of the observable universe by volume. 80%. The vast majority of the universe is not filled with galaxies and stars and planets. It is filled with almost nothing. The places where matter congregates, the galaxies, the clusters, the superclusters, are the minority. They cling to the thin walls and filaments between the voids, like soap film on the surface of a bubble. The universe, at its largest scale, looks like foam, enormous bubbles of emptiness separated by impossibly thin membranes of matter. And here is something even more unsettling. You live inside a void. The Milky Way sits inside what researchers call the KBC void, also known as the local hole. Named after astronomers Ryan Keenan, Amy Barger, and Lennox Cowie, who studied it in 2013. The KBC void is a region of below-average galaxy density, roughly 2 billion light-years across. 2 billion light-years. That is more than 6 times the width of the Boots void. We are not in a normal part of the universe. We are not in a bustling galactic neighborhood. We are in a relatively empty zone, an underdense region where 15 to 50% fewer galaxies exist than in the surrounding space. The Milky Way sits within a few 100 million light-years of the void center. We are, in a very real sense, residents of the cosmic suburbs, the places where the streetlights thin out and the houses are far apart. And this is not just a curiosity. The KBC void may have real consequences for our understanding of the universe. Some researchers have proposed that living inside a large underdense region could be contributing to the Hubble tension, the crisis we discussed in Chapter 1. The reasoning goes like this. Galaxies inside a void experience a gravitational pull from the denser regions outside the void. This pull accelerates the local expansion of space, making the universe appear to be expanding faster in our neighborhood than the cosmic average. If the KBC void is real, and if we are near its center, our local measurements of the expansion rate would naturally come out higher than the value derived from the early universe. The discrepancy would not be a sign of broken physics. It would be a sign that our address in the cosmos is slightly unusual. Data presented at the National Astronomy Meeting in 2025 using baryon acoustic oscillation measurements suggested that a void model is roughly 100 million times more likely than a void-free model consistent with Planck cosmology value. Other researchers dispute this. The question remains open, but the implication is striking. The biggest crisis in cosmology might be partly caused by the fact that we happen to live in a relatively empty part of the universe. Our view of reality might be distorted by our location. But where did the voids come from? Why is the universe organized this way? Why is 80% of the cosmos a desert? The answer reaches back to the very beginning, to the first fractions of a second after the Big Bang. When the universe was born, it was not perfectly uniform. It was almost uniform, almost perfectly smooth and hot and dense, but not quite. Quantum mechanics, the physics of the subatomic, ensured that tiny random fluctuations existed in the density of matter and energy. These fluctuations were unimaginably small, variations of roughly 1 part in 100,000. If the early universe had been a perfectly calm ocean, these fluctuations would have been ripples smaller than a millimeter on a surface stretching thousands of kilometers. But gravity is patient, and gravity is relentless. Over billions of years, gravity amplified those tiny differences. Regions that were slightly denser than average pulled a little more matter toward themselves. Regions that were slightly less dense lost matter to their denser neighbors. It was a cosmic feedback loop. The rich got richer, the poor got poorer. Dense regions became denser, empty regions became emptier. Over time, the slight variations in density grew into the vast structures we see today. Matter concentrated into thin sheets and filaments. The spaces between those sheets expanded and emptied out, becoming the voids. The universe, shaped by the same quantum jitter that governs the behavior of subatomic particles, organized itself into a web. A vast interconnected network of matter and emptiness stretching across the entire observable universe. The cosmic web is shaped more by what is missing than by what is there. The voids are not holes punched into an otherwise solid universe. They are the original state, the default condition. Emptiness is the norm. Matter is the exception. The galaxies, the stars, the planets, the atoms that make up your body, all of it exists on the thin, glowing threads between enormous bubbles of nothing. If 80% of the universe is void, what fills the 20% that remains? The answer is a structure so vast and so intricate that it took decades to discover. A network so enormous that it spans the entire observable universe. And in 2025, for the first time in human history, we photographed a piece of it. A single strand of the largest structure in existence. A highway of gas and dark matter stretching 3 million light-years between two ancient galaxies. A strand of something called the cosmic web. And what it revealed is that the universe is not a random scattering of galaxies. It is a machine. A living, flowing, spinning machine built on an invisible scaffold that we are only now beginning to see. Chapter 4. The Web. The universe is not a random scattering of galaxies floating through space like dust motes in a dark room. It has a skeleton, an architecture, a vast interconnected network of filaments and nodes and voids that stretches across the entire observable universe and beyond. Scientists call it the cosmic web, and it is the largest structure in existence. The term cosmic web was coined in 1996 by the cosmologist Richard Bond, but the idea behind it had been building for years. As galaxy surveys became more detailed throughout the 1980s and 90s, astronomers noticed that galaxies were not evenly distributed through space. They clustered, they formed chains, they lined up along invisible corridors, and between those corridors lay the vast empty voids. The pattern was unmistakable. At the largest scales, the universe had organized itself into something that looked like a three-dimensional spiderweb. Bright filaments of galaxies connecting massive nodes called galaxy clusters, with dark, empty voids filling the space between. The filaments are enormous. Individual strands can stretch hundreds of millions of light-years. They are made of dark matter, gas, and galaxies, all pulled together by gravity into elongated structures that serve as highways connecting the densest regions of the cosmos. At the intersections where filaments meet, galaxy clusters form. These are the nodes of the web, the largest gravitationally bound structures in the universe. They contain hundreds or thousands of galaxies, vast clouds of superheated gas, and enormous halos of dark matter. Our own local group, the small collection of roughly 100 galaxies that includes the Milky Way and the Andromeda Galaxy, sits on a filament. This filament connects the Fornax cluster to the Virgo cluster. We are not at a node, we are not at an intersection. We are on a backroad between two galactic cities. For decades, the cosmic web existed primarily in computer simulations and mathematical models. Supercomputers could simulate the evolution of the universe from the Big Bang to the present and consistently produced web-like structures that matched the observed distribution of galaxies. The theory was solid, the models were beautiful, but directly imaging a filament, capturing the faint glow of the gas and matter within it, remained beyond our reach. The gas in the filaments is incredibly diffuse. Hydrogen, the most abundant element in the universe, emits only the faintest glow when it is spread across millions of light years. Detecting that glow is like trying to photograph a candle from the other side of a continent. Then, in 2025, an international team led by Davide Tornotti, a doctoral student at the University of Milano Bicocca, in collaboration with the Max Planck Institute for Astrophysics, achieved what decades of astronomers had hoped for. They captured the first high-definition, direct image of a cosmic web filament. The filament they imaged stretches 3 million light-years between two galaxies, each hosting an active, supermassive black hole. These galaxies sit at a redshift of 3, meaning the light from this filament has been traveling through space for nearly 12 billion years. When this filament was glowing, the universe was only about 2 billion years old. We are looking at the cosmic web in its youth. The team used the multi-unit spectroscopic explorer, known as MUSE, mounted on the European Southern Observatory Very Large Telescope in Chile. MUSE is an extraordinary instrument. It collects spectra for every pixel in its field of view, allowing astronomers to separate the filament faint hydrogen emission from background noise. But even with MUSE, the task required over 150 hours of observation focused on the same patch of sky. 150 hours of a world-class telescope staring at one point in the universe, gathering photon after photon, building an image from the faintest light imaginable. The result was published in Nature Astronomy, and it was stunning. The image showed the diffuse gas contained within the filament, stretching between the two galaxies like a glowing bridge. The researchers could trace the boundary between the gas residing within the galaxies and the material contained within the cosmic web itself. For the first time, the connection between a galaxy and the web that feeds it was directly observed. And when they compared their image to the supercomputer simulations from the Max Planck Institute, the agreement was striking. The shape, the density, the brightness profile of the observed filament matched the predictions almost exactly. The simulations had been right all along. The cosmic web is real. It looks exactly as the models predicted, and now we have a photograph to prove it. But the cosmic web is not static. It is not a frozen scaffold holding galaxies in place. It is alive, dynamic, moving. In late 2025, researchers at the University of Oxford published a remarkable discovery in the monthly notices of the Royal Astronomical Society. Using data from the Meerkat radio telescope in South Africa, they found one of the largest rotating structures ever observed. A chain of 14 galaxies embedded in a cosmic filament 5.5 million light-years long. All 14 galaxies are spinning in the same direction. The entire filament, a structure millions of light-years across, is rotating. This was unexpected. The conventional picture of filaments was that they were passive structures, gravitational scaffolding that matter fell onto and flowed along. But the Oxford discovery showed that filaments are actively transferring angular momentum, the energy of rotation, across vast distances. They are not just highways, they are rivers. Rivers of gas, matter, and rotational energy that flow into galaxies at the nodes, feeding them, spinning them, shaping them. The cosmic web is the circulatory system of the universe. It is the network through which matter and energy flow, from the emptiness of the voids to the dense, crowded intersections where galaxies are born and grow. Without the web, galaxies would have no supply line, no raw material. They would exhaust their gas reserves and slowly fade. The web keeps them alive. And the web itself is built on something we cannot see, something that makes up 85% of all matter in the universe, something that does not emit light, does not absorb light, does not reflect light. Something that we know exists only because of its gravitational influence on everything around it. The dark matter that forms the invisible skeleton of the cosmic web is the single most abundant form of matter in the universe, and we have never directly detected it. Every filament, every node, every galaxy cluster in the cosmic web sits within a halo of dark matter. The dark matter came first. It collapsed under gravity long before ordinary matter could, forming the scaffolding on which gas and eventually stars would accumulate. The galaxies we see are just the luminous frosting on an invisible cake. The real structure, the real architecture of the universe is dark. In 2024, researchers at Yonsei University achieved a milestone. Using data from the Subaru telescope, they made the first detection of dark matter sitting directly on cosmic web filaments in the Coma cluster region. They used gravitational lensing, the bending of light from distant background galaxies caused by the mass of the filament, to map the dark matter distribution along the strands of the web. The dark matter was there, right where the models predicted, invisible but heavy, shaping everything. The cosmic web is the universe's real structure, not the galaxies, not the stars, not the planets. Those are decoration. The web is the frame, and the frame is built from darkness. It is held together by a substance we cannot see, and powered by a force we cannot explain. And when you zoom out far enough to see the web in its entirety, you realize something that changes how you think about reality itself. You are not living in a universe scattered with galaxies. You are living on a strand of the web, one thin glowing thread in a network of threads, surrounded on all sides by the vast, cold, silent emptiness of the voids, clinging to a filament like dew on a spider web. And the spider, if there is one, is invisible. Chapter 5. The Dark Scaffold. Here is a number that should make you uncomfortable: 5%. That is how much of the universe you can see. That is how much of the universe is made of the matter you learned about in school. Protons, neutrons, electrons, atoms, molecules, stars, planets, gas clouds. Everything you have ever touched, tasted, seen, or measured with any scientific instrument ever built. All of it, 5%. The remaining 95% is made of two things. 27% is dark matter, 68% is dark energy. Together, they dominate the cosmos completely, and we do not understand either of them. Let us start with dark matter. It was first proposed in the 1930s by the Swiss astronomer Fritz Zwicky. He was studying the Coma cluster, a massive collection of galaxies roughly 320 million light-years from Earth. He measured the speeds at which the galaxies in the cluster were moving and found something wrong. They were moving too fast, far too fast for the visible matter in the cluster to hold them together gravitationally. The galaxies should have flown apart long ago. Something invisible was providing the extra gravitational glue. Zwicky called it Dunkel Materie, dark matter. For decades, the idea was largely ignored. It seemed too strange, too speculative. Then in the 1970s, the American astronomer Vera Rubin made the same discovery on a smaller scale. She was measuring the rotation speeds of stars within spiral galaxies. According to Newtonian gravity, stars at the edges of a galaxy should orbit more slowly than stars near the center, just as the outer planets in our solar system orbit more slowly than the inner ones. But Rubin found that the rotation curves were flat. Stars at the edges of galaxies were moving just as fast as stars near the center. The only explanation was that a massive halo of invisible matter extended far beyond the visible disk of each galaxy, providing the gravitational pull needed to keep those outer stars in orbit. Since then, the evidence for dark matter has piled up from every direction. Galaxy clusters bend light from objects behind them more strongly than their visible mass can account for, a phenomenon called gravitational lensing. The cosmic microwave background contains patterns that only make sense if dark matter existed in the early universe, creating the gravitational wells into which ordinary matter fell. And the cosmic web itself would not form without dark matter. Simulations that include only ordinary matter produce a universe that looks nothing like what we observe. Add dark matter and the web emerges. The filaments form, the voids open, the galaxies cluster at the nodes. Dark matter is not a minor ingredient. It is the main ingredient. It makes up 85% of all matter in the universe. And yet we do not know what it is. Dozens of experiments around the world are searching for dark matter particles. Underground detectors in old mines, shielded from cosmic rays by kilometers of rock. Particle accelerators like the Large Hadron Collider at CERN, smashing protons together at nearly the speed of light, hoping to create dark matter particles in the debris. Space telescopes looking for the gamma-ray signatures of dark matter particles annihilating each other. None of these experiments have produced a confirmed detection. The most popular candidates, a class of hypothetical particles called weakly interacting massive particles, have stubbornly refused to appear. After decades of searching, we know dark matter is there. We can map its distribution, we can measure its effects, but we cannot find the particle. Now let us turn to the even stranger member of the dark family, dark energy. In 1998, two teams of astronomers made a discovery that would win them the Nobel Prize in Physics in 2011 and shake the foundations of cosmology. They were studying a particular type of exploding star called a Type Ia supernova. These supernovae are useful because they all reach roughly the same peak brightness, which makes them excellent distance markers. By measuring how bright a Type Ia supernova appears from Earth and comparing that to how bright it actually is, astronomers can calculate how far away it is. Both teams, the Supernova Cosmology Project and the High Z Supernova Search Team, were using these supernovae to measure the expansion history of the universe. The expectation was straightforward. The expansion of the universe should be slowing down. Gravity, the attractive force between all matter, should be gradually pulling everything back together, decelerating the expansion that began at the Big Bang. The results said otherwise. The distant supernovae were dimmer than expected. They were farther away than they should have been. The expansion of the universe was not slowing down, it was speeding up. Something was pushing space apart. Something was overcoming the gravitational attraction of all the matter in the universe and accelerating the expansion. Something with no obvious source, no known mechanism, no precedent in physics. Scientists named it dark energy, a name that admitted their ignorance. It is dark because we cannot see it. It is energy because it does something. And that something is tearing the universe apart. Dark energy is not a force in the traditional sense. It does not push galaxies apart the way a rocket pushes away from Earth. Instead, it is a property of space itself. It causes space to expand, and the more space there is, the stronger its effect becomes. As the universe grows, more space is created, which generates more dark energy, which causes more expansion, which creates more space. It is an accelerating cycle, and it is winning. The effects are profound. Distant galaxies are receding from us faster and faster. Some galaxies beyond a certain distance are already receding faster than the speed of light. Not because they are moving through space faster than light, that is impossible, but because the space between us and them is expanding faster than light can cross it. Light emitted from those galaxies right now will never reach us. They are lost to us forever, carried beyond the horizon by the expansion of the universe itself. Dark energy makes up 68% of the total energy content of the universe. Dark matter makes up 27%. Ordinary matter, everything you can see and touch, everything that makes up every star, every planet, every atom in your body, makes up 5%. 5% we understand 5% of what the universe is made of. The greatest structure ever discovered, the cosmic web, is built on a scaffold of dark matter that we have never directly detected, powered by dark energy that we cannot explain. And everything visible in the night sky is a thin, luminous film stretched over an abyss of invisible forces. Every telescope, every experiment, every spacecraft we have ever built has been studying the 5%. The decoration, the frosting, the visible crust on an invisible machine of staggering complexity. And if we barely understand what the universe is made of, how can we trust our map of how big it is? How can we be confident in our models when 95% of reality remains unexplained? The answer is that our confidence is wobbling. Our models are straining under the weight of new observations, and the map, as we are about to see, is starting to contradict itself. Because somewhere out there, hidden behind the dust and gas of our own galaxy, something enormous is pulling us. The Milky Way and 400 other galaxies are hurtling through space at over 2 million kilometers per hour toward a region of space we cannot fully see. A gravitational anomaly so powerful that it dominates the motion of everything within hundreds of millions of light years. And we still do not know exactly what it is. Chapter 6. The Invisible Hand. The Milky Way is not sitting still. Nothing in the universe is sitting still. Everything is moving. Planets orbit stars. Stars orbit the center of their galaxies. Galaxies orbit each other in clusters. Clusters flow along the filaments of the cosmic web. But above and beyond all of these motions, there is something else. A pull. A vast, persistent, gravitational pull dragging the Milky Way and roughly 400 other galaxies in a specific direction at an astonishing speed. 600 kilometers per second, that is 2.2 million kilometers per hour. Every second, the Milky Way moves 600 kilometers closer to a region of space in the direction of the constellation Centaurus, roughly 150 to 250 million light-years away. We are not drifting. We are racing. And the destination is something we can barely see. Scientists call it the Great Attractor. The Great Attractor was first identified in the 1980s by a team of 7 astronomers, later nicknamed the Seven Samurai. Led by Alan Dressler, they were mapping the peculiar velocities of galaxies, the velocities that deviate from the smooth expansion of the universe. When they plotted these motions, they found that a large swath of the cosmos was streaming in the same direction. Hundreds of galaxies, all converging toward a single gravitational center. Something was pulling them, something massive, something that did not show up in the optical surveys. The problem is location. The Great Attractor lies behind what astronomers call the zone of avoidance. This is the region of the sky that is blocked from our view by the disk of the Milky Way itself. Our own galaxy, the very platform from which we observe the universe, sits directly in the line of sight. The dust, gas, and dense fields of stars in the Milky Way plane absorb and scatter the light from whatever lies behind it. It is like trying to see a distant mountain through a fog bank. You know something is there because you can feel its gravitational influence, but you cannot get a clear picture. Over the decades, astronomers have used other wavelengths of light to peer through the zone of avoidance. X-ray surveys in the 1990s revealed the Norma cluster, also known as Abell 3627, sitting at the approximate position of the Great Attractor. The Norma cluster is a massive galaxy cluster, but when they estimated its mass, it came up short. Only about 1/10 of the gravitational pull needed to explain the observed motions. The Norma cluster alone could not be the Great Attractor. Something even larger had to be behind it. And something is. Behind the Great Attractor, farther away and far more massive, lies the Shapley supercluster, also known as the Shapley concentration. It is one of the most massive structures in the observable universe. A dense collection of galaxy clusters and superclusters, roughly 650 million light-years from Earth. Some researchers now believe that the Great Attractor is not the true destination at all. It is more like a waypoint, a gravitational rest stop on the road to the Shapley supercluster. The real pulling force may be distributed across this much larger structure. In 2014, a breakthrough changed the picture entirely. A team led by Brent Tully of the University of Hawaii published a paper in the journal Nature that redefined the cosmic map. Using galaxy flow data, they mapped the gravitational basin in which the Milky Way and thousands of other galaxies reside. They called this basin the Laniakea supercluster. Laniakea is Hawaiian for immense heaven. It spans 520 million light-years and contains approximately 100,000 galaxies. The Great Attractor sits at its gravitational center. Every galaxy within Laniakea is flowing toward this center, pulled by the combined gravitational influence of the dark matter and visible matter concentrated there. We are inside Laniakea. We are one of its 100,000 galaxies. We are falling toward its center. But here is the paradox. We will never get there, because the universe is expanding, and that expansion is accelerating. Dark energy, the mysterious force that fills 68% of the cosmos, is stretching the space between galaxy clusters faster than gravity can pull them together. The Great Attractor is pulling us. But the expansion of space is pulling us apart. We are approaching the attractor at 600 kilometers per second, but the space between us and it is stretching at a rate that will eventually exceed our approach speed. The Milky Way is on a journey it will never complete. We are falling toward a destination we will never reach. Gravity gives us direction. Dark energy denies us arrival. It is motion without purpose. An infinite approach to an unreachable center. And this is the fundamental character of the universe at its largest scales. Everything is in motion. Everything is connected by gravity. But expansion wins in the end. Over billions of years, the universe will stretch apart. Galaxy clusters that are not gravitationally bound to each other will drift beyond each other cosmic event horizons. They will become invisible to one another, unreachable, lost. And yet, for now, in this brief cosmic moment, the architecture holds together. The web is intact. The filaments are flowing. The nodes are growing. The Great Attractor pulls, and the galaxies answer. We are part of a structure, a vast interconnected gravitational organism that spans hundreds of millions of light-years. We now have the pieces, the voids, the filaments, the dark scaffold, the invisible hand. It is time to assemble the full picture, to zoom out as far as we can and see where we sit in the grand cosmic hierarchy, to write our full address from Earth to the edge of the observable universe. And each layer of that address will dwarf the last in a way that is almost impossible to process, because the universe is not just big, it is structured to be big. It is organized, layered, nested, each container impossibly larger than the one before it. Your cosmic address starts here, on a small rocky planet orbiting an ordinary star, and it ends at the edge of everything we can see, a boundary so distant that light from the other side has been traveling for 13.8 billion years and has still not reached us. But even that boundary is not the end. It is not even close. The observable universe, all 93 billion light-years of it, may be a keyhole, and the room behind it may be unimaginably, terrifyingly larger than anything we have yet calculated. Let us build the address, step by step, layer by layer, and see how small we really are. Chapter 7. Your Cosmic Address. Let us build it from the ground up. Your cosmic address, every layer larger than the last, every step a revelation in scale. You are on Earth, a rocky planet 12,742 kilometers in diameter. It orbits a star we call the Sun, a middle-aged yellow dwarf star, roughly 4.6 billion years old. The Sun is one star among 250 billion in the Milky Way galaxy. It is not special. It is not central. It is a perfectly ordinary star in a perfectly ordinary part of the galaxy. The Sun and its planets make up the solar system. The solar system sits within a small region of diffuse interstellar gas called the local interstellar cloud. This cloud is about 30 light-years across, and the Sun has been passing through it for roughly 44,000 years. The local interstellar cloud itself sits inside a much larger structure called the local bubble. The local bubble is a region of hot, low-density gas, roughly 1,000 light-years across. It was created by a series of supernova explosions over the past 10 to 20 million years. Those explosions blasted away the denser interstellar medium and inflated a cavity of thin, hot plasma. We are inside that cavity. The local bubble sits within one of the Milky Way spiral arms, specifically the Orion arm, also called the Orion spur. It is a minor arm, a bridge between two larger spiral arms, the Sagittarius arm and the Perseus arm. The Orion arm is roughly 3,500 light-years wide and 10,000 light-years long, and the Orion arm is one feature of the Milky Way galaxy. Our galaxy is a barred spiral galaxy, roughly 100,000 light-years in diameter and about 1,000 light-years thick at the disk. It contains an estimated 250 billion stars and likely more planets than stars. At its center sits a supermassive black hole called Sagittarius A star, with a mass of roughly 4 million times that of the Sun. Until 1920, most astronomers believed the Milky Way was the entire universe. The great debate of that year between Harlow Shapley and Heber Curtis centered on whether the fuzzy patches called spiral nebulae were structures within our galaxy or separate galaxies entirely. When Edwin Hubble used Cepheid variable stars to prove that the Andromeda Nebula was a separate galaxy, millions of light-years away, the universe expanded overnight, not physically, conceptually. Humanity realized that our galaxy was one island in an archipelago of galaxies stretching as far as telescopes could see. Now let us zoom out further. The Milky Way is not alone. It is one of roughly 100 galaxies in a gravitationally bound collection called the Local Group. The Local Group spans approximately 10 million light-years. Its two largest members are the Milky Way and the Andromeda Galaxy, which is roughly 2.5 million light-years away and contains about 1 trillion stars. Andromeda and the Milky Way are on a collision course. In roughly 4.5 billion years, the two galaxies will merge in a slow gravitational dance that will reshape both. The Local Group also contains the Triangulum Galaxy, roughly 60 smaller galaxies, and numerous dwarf galaxies. Together, these galaxies orbit their common center of gravity, bound together by the gravitational influence of their combined mass, most of which is dark matter. The Local Group is part of a much larger structure called the Virgo supercluster. The Virgo supercluster contains roughly 100 galaxy groups and clusters, spread across 110 million light-years. At its heart is the Virgo cluster, a massive collection of over 1,300 galaxies, roughly 54 million light-years from Earth. The Virgo cluster dominates the supercluster gravitationally. We are on its outskirts, a small group orbiting at the edge of a much larger gravitational kingdom. But even the Virgo supercluster is just a lobe of something far grander. In 2014, Brent Tully and his team revealed Laniakea. The Laniakea supercluster encompasses the Virgo supercluster and much more. It spans 520 million light-years and contains roughly 100,000 galaxies, all of them flowing toward the Great Attractor at its gravitational center. Laniakea is our true neighborhood, the gravitational basin in which we reside. And Laniakea is part of an even larger structure, the Pisces-Cetus supercluster complex. This is a galactic filament, one of the strands of the cosmic web, stretching approximately 1 billion light-years. 1 billion light-years. It is one of the largest coherent structures ever identified, a thread of galaxy clusters and superclusters, including Laniakea, strung along a single filament of the web. And all of this, the Pisces-Cetus supercluster complex, Laniakea, the Virgo supercluster, the local group, the Milky Way, the Sun, the Earth, all of it is a tiny fragment of the observable universe. The observable universe is a sphere centered on Earth with a diameter of approximately 93 billion light-years. It contains an estimated 2 trillion galaxies, 10 to the power of 24 stars. More stars than all the grains of sand on every beach and desert on the planet combined. The Pisces-Cetus supercluster complex, one of the largest structures we know, stretches 1 billion light-years. The observable universe is 93 billion light-years across. Our largest known structure is roughly 1% of the observable universe diameter. Think about that. The filament that contains our supercluster, that contains our galaxy cluster, that contains our galaxy, that contains our star, that contains our planet, is 1% of the observable universe. We are small beyond comprehension. A speck within a thread within a web, within a sphere so vast that light itself, traveling at 300,000 kilometers per second, takes 13.8 billion years to cross it. And 93 billion light-years sounds like everything. It sounds like the whole story. It sounds like the end of the road. It is not. 93 billion light-years is not the size of the universe. It is the size of the part we can see, the observable universe. The portion from which light has had time to reach us since the Big Bang. Beyond the edge of the observable universe, there is more, vastly more. The observable universe may be a keyhole, a tiny window looking out onto a room of incomprehensible size. To understand why, we need to understand what happens at the edge, what we see when we look as far as light can carry us, and what lies beyond the last photon that will ever reach our eyes. The edge of the observable universe is not a wall. It is not a boundary in space. It is a boundary in time, a boundary defined by the speed of light and the age of the cosmos. And approaching it will teach us something about the universe that is both beautiful and deeply unsettling. The observable universe is not just a sphere of galaxies. It is a prison, a cage made of expanding space from which no signal, no message, no spacecraft could ever escape. A cage that is getting larger and smaller at the same time. Chapter 8. The Edge of Sight. Here is a misconception that almost everyone carries. The universe is 13.8 billion years old, so the farthest we can see must be 13.8 billion light-years in each direction. That makes intuitive sense. Light travels at 1 light-year per year. The universe has existed for 13.8 billion years, so the light has had time to travel 13.8 billion light-years. Simple and wrong. The farthest we can see is not 13.8 billion light-years. It is roughly 46 billion light-years in every direction. The observable universe has a diameter of approximately 93 billion light-years. How is that possible if the universe is only 13.8 billion years old? Because space itself has been expanding the entire time. When a distant galaxy emitted its light 13 billion years ago, that galaxy was much closer to us than it is now. The light began its journey, but while it was traveling, the space between us and that galaxy was stretching. The galaxy was being carried farther and farther away by the expansion of the universe. By the time the light finally reaches our telescopes, the galaxy that emitted it is no longer 13 billion light-years away. It is now roughly 46 billion light-years away. It has been receding from us the entire time the light was in transit. This is the difference between what astronomers call the light travel distance and the comoving distance. The light travel distance is how long the light has been traveling, 13.8 billion years at most. The comoving distance accounts for the expansion that occurred during that travel time. The edge of the observable universe, in comoving terms, is about 46.1 billion light-years away in every direction. That gives us a sphere 93 billion light-years across. At the very edge of this sphere, we do not see galaxies. We see something older, something more fundamental. We see the cosmic microwave background. The cosmic microwave background, or CMB, is the oldest light in the universe. It was released approximately 380,000 years after the Big Bang, during an event called recombination. Before recombination, the universe was so hot and dense that electrons and protons could not combine to form atoms. Free electrons scattered photons constantly, making the universe opaque. Light could not travel freely. It was trapped in a fog of superheated plasma. Then, as the universe expanded and cooled, the temperature dropped below roughly 3,000 degrees. Electrons were captured by protons. Neutral hydrogen atoms formed. And suddenly, the universe became transparent. Photons that had been bouncing around in the plasma were released. They flew outward in every direction. Those photons have been traveling ever since, cooling and stretching as the universe expanded, their wavelengths elongating from visible light to microwaves. In 1964, Arno Penzias and Robert Wilson at Bell Labs accidentally detected this radiation while working on a microwave antenna. They found a faint, uniform hiss of microwave radiation coming from every direction in the sky. They could not get rid of it. It was not interference. It was not equipment noise. It was the echo of the Big Bang, the afterglow of creation. It earned them the Nobel Prize in Physics in 1978. The CMB is the farthest thing we can see with light. It is a wall of radiation surrounding us in every direction, marking the moment the universe first became transparent. Beyond it, in the time before recombination, the universe was opaque. No light from that era can reach us. The CMB is the ultimate horizon for electromagnetic observation. Everything beyond it is invisible to every telescope ever built or ever conceived that uses light. There is a slight extension possible. Neutrinos, the ghostly subatomic particles that barely interact with matter, would have decoupled from the primordial plasma earlier than photons. A cosmic neutrino background theoretically exists, carrying information from when the universe was just 1 second old. If we could detect it, it would extend our view slightly further, to a comoving distance of roughly 46.31 billion light-years. But detecting the cosmic neutrino background is beyond our current technology. For now, the CMB is the wall. But there is something even more confining than the CMB, something that defines the absolute limit of what we will ever see, no matter how long we wait or how good our instruments become. It is called the cosmic event horizon. Because the expansion of the universe is accelerating, driven by dark energy, there are regions of space that are receding from us faster than the speed of light. Right now, as you listen to this, galaxies beyond a certain distance are being carried away by the expansion of space at velocities that exceed 300,000 kilometers per second. This does not violate Einstein's theory of relativity. Relativity says that nothing can travel through space faster than light, but it places no limit on how fast space itself can expand. Space is not a thing moving through a medium. Space is the medium, and it can stretch as fast as it likes. Any light emitted by those galaxies right now will never reach us. The photons leave the galaxy and begin traveling toward us at the speed of light. But the space between us is expanding faster than the photons can cross it. The photons fall behind. They are running on a treadmill that is accelerating. They will never arrive. This creates a boundary, the cosmic event horizon. Beyond it, no signal can reach us. No light, no radio wave, no gravitational wave, nothing. It is the ultimate prison wall, the edge of our causal universe. Everything beyond the cosmic event horizon is and will forever be, entirely disconnected from us. We cannot see it. We cannot communicate with it. We cannot interact with it in any way. There is a future visibility limit. Over time, light from regions slightly beyond our current view will arrive, as those photons have been traveling toward us since before the expansion accelerated them beyond reach. This limit extends to objects currently about 61 billion light-years away. Over billions of years, our observable volume will roughly double. But that is the maximum. The final view. After that, the accelerating expansion will ensure that no new light from beyond that boundary ever arrives. And as the expansion continues to accelerate, galaxies that are currently visible will eventually cross the event horizon and disappear. One by one, over trillions of years, the galaxies outside our local gravitationally bound group will redshift into invisibility. Their light will stretch to wavelengths too long to detect. They will fade like ships sailing over the horizon of an ocean that is growing faster than they can return. In the far, far future, the only galaxies visible from our vantage point will be the few dozen in our own local group, which are gravitationally bound tightly enough to resist the expansion. To a civilization living in that distant era, the universe will appear to be a single galaxy floating in an infinite black void. They will have no way of knowing that trillions of other galaxies once filled the sky. No way of detecting the cosmic microwave background, which will have redshifted to undetectable wavelengths. No way of deducing the Big Bang. Their cosmology will be wrong, through no fault of their own, because the evidence will have been carried beyond their reach by the expansion of space. We live in a privileged time. Right now, in this narrow window of cosmic history, we can still see the CMB. We can still detect distant galaxies. We can still piece together the story of the Big Bang and the evolution of the universe. In the distant future, that will no longer be possible. The universe is slowly, inexorably, hiding its own history. So, this is our cage, 93 billion light-years across, bounded by the cosmic microwave background in one sense and the cosmic event horizon in another. Everything we know, everything we have ever measured, everything our instruments can detect, exists within this sphere. And everything beyond it is a mystery. But here is the question that matters most. How big is everything beyond it? Is the unobservable universe slightly larger than what we can see? Or is it incomprehensibly, terrifyingly, absurdly larger? The answer depends on which physicist you ask. And some of the answers will make you feel smaller than anything in this documentary has so far. But before we go beyond the wall, we need to deal with what is happening on this side of it, because the telescope that was supposed to confirm our understanding of the early universe has instead shattered it, and the crisis it has revealed is only getting worse. Chapter 9. What James Webb is really showing us. The James Webb Space Telescope launched on December 25, 2021. It was the most expensive, most complex, and most anticipated scientific instrument ever built. 25 years in development, $10 billion in cost, a 6.5-meter gold-plated mirror designed to capture infrared light from the farthest reaches of the universe. It was positioned at the second Lagrange point, roughly 1.5 million kilometers from Earth, where it orbits the Sun in gravitational lockstep with our planet. It unfurled its sunshield, cooled its instruments to near absolute zero, and turned its golden eye toward the darkness. What it found there has shaken cosmology to its foundations. In January 2026, NASA announced the confirmed detection of the most distant galaxy ever observed, MOM-Z14. The name comes from the MIRAGE or Miracle Survey, a spectroscopic program designed to confirm high redshift galaxy candidates. The Z14 refers to the galaxy approximate redshift. Spectroscopic analysis using the James Webb Near Infrared Spectrograph confirmed a redshift of 14.44, That number means the light from MOM-Z14 has been traveling for over 13.5 billion years. We are seeing this galaxy as it existed just 280 million years after the Big Bang, when the universe was 2% of its current age, when the cosmos was still in its infancy, still emerging from the Dark Ages, the period before the first stars and galaxies lit up. And MOM-Z14 should not look the way it does. According to the models that existed before James Webb launched, galaxies at this epoch should be dim, small, simple collections of primordial gas, just beginning to form their first stars. The universe was too young for anything complex. There had not been enough time for large-scale star formation, not enough time for heavy elements to accumulate, not enough time for galaxies to grow bright and structured. MOM-Z14 defies every one of those expectations. It is remarkably luminous, with an absolute ultraviolet magnitude of -20.2. It is extremely compact, just 74 parsecs in effective radius. That is roughly 240 light-years. For comparison, the distance from the Sun to the center of the Milky Way is about 26,000 light-years. This galaxy is tiny, but it is blazing. Its spectrum reveals elevated nitrogen emission. Nitrogen is an element that normally requires multiple generations of stars to produce. Massive stars fuse hydrogen and helium in their cores, then explode as supernovae, scattering heavier elements into the surrounding gas. New stars form from that enriched gas and produce even heavier elements. Over many cycles, nitrogen accumulates, but 280 million years is not enough time for many stellar generations. The presence of nitrogen in MOM-Z14 suggests something unusual is happening. The research team proposed that supermassive stars, far more massive than anything in the nearby universe, may have formed in the dense environment of the early cosmos and produced nitrogen through exotic nuclear processes far more rapidly than normal stellar evolution allows. And there is another anomaly. MOM-Z14 appears to have partially ionized its surrounding environment. The early universe was filled with neutral hydrogen gas, a thick fog that blocked ultraviolet light. The epoch of reionization is the period when the first stars and galaxies produced enough ultraviolet radiation to ionize this fog and make the universe transparent. Most models predict that at redshift 14, the universe should be almost entirely neutral, nearly 100% fog, but MOM-Z14 surroundings show evidence of partial ionization. This tiny galaxy, just 280 million years after the Big Bang, has already begun clearing the fog around it, something that models said should not be possible at this epoch. Rohan Naidu, the lead author and an astrophysicist at the Massachusetts Institute of Technology, Kavli Institute for Astrophysics and Space Research, said it plainly. With Webb, we are able to see farther than humans ever have before, and it looks nothing like what we predicted, which is both challenging and exciting. MOM-Z14 is not an isolated case. It is the most extreme example of a pattern that has been building since James Webb began observations. The telescope has discovered over 100 bright galaxies at redshifts above 10, in an era where the pre-launch consensus models predicted essentially none. The number density of bright galaxies at redshift 14 to 15 is more than 100 times larger than those models expected. 100 times, not 10% more. Not double, 100 times. Among the most striking discoveries is Zhulong, a galaxy identified by an international team and published in Astronomy and Astrophysics in 2025. Zhulong sits at a redshift of approximately 5.2, meaning we see it as it was roughly 1 billion years after the Big Bang. That is older than MOM-Z14 by about 700 million years. But what makes Zhulong extraordinary is its maturity. It is an ultra-massive grand design spiral galaxy. It has spiral arms, a mature central bulge, a total stellar mass of roughly 100 billion solar masses. It looks like a galaxy that has had billions of years to evolve. It had 1 billion. Galaxies like Zhulong are not supposed to exist that early. Spiral structure requires dynamical settling. Central bulges require repeated mergers and gas accretion over extended periods. Assembling 100 billion solar masses of stars in 1 billion years pushes the limits of what star formation physics can achieve. And yet there it is, fully formed, beautiful, impossible. Jacob Shen, a postdoctoral researcher at MIT and member of the MOMAM Z14 team, captured the mood of the field when he said, "There is a growing chasm between theory and observation related to the early universe, which presents compelling questions to be explored going forward." A growing chasm. That is diplomatic language for something more alarming. The standard model of cosmology, lambda CDM, is being challenged at its foundations. Not by fringe theories, not by speculative philosophy, by data, by the most powerful telescope ever built, doing exactly what it was designed to do, looking at the early universe and reporting what it sees. To be clear, the Big Bang itself is not in question. The evidence for the Big Bang is overwhelming and comes from multiple independent sources. The cosmic microwave background, the observed expansion of the universe, the abundance of light elements like hydrogen, helium, and lithium, which match the predictions of Big Bang nucleosynthesis. These pillars stand firm. What is breaking is the timeline. The sequence of events that lambda CDM predicts should follow the Big Bang. According to the model, galaxies should form slowly, growing through mergers and gradual gas accretion over billions of years. Small galaxies should form first, then merge into larger ones. Bright, massive, structured galaxies should not appear until the universe is well into its adolescence, several billion years old at minimum. James Webb is showing us something different. Galaxies are forming faster than the models allow. They are brighter than they should be, more massive, more chemically enriched, more structured. They look old when they should look young. Proposed solutions are multiplying. Some researchers suggest that star formation in the early universe was far more efficient than models assumed. Perhaps the conditions of the dense early cosmos allowed gas to collapse into stars at rates that vastly exceeded anything in the nearby universe. Others invoke early dark energy, a hypothetical phase of extra dark energy that existed briefly in the first few 100 million years, accelerating the growth of structures. Others suggest modifications to the physics of dark matter, perhaps allowing it to interact with itself in ways that enhanced gravitational collapse in the early universe. Some have even proposed new particle physics entirely. None of these solutions fully work. None can explain all of the anomalies without creating new problems. The Tensions in Cosmology 2025 conference, held in Corfu, Greece, brought together over 130 researchers to address the growing list of discrepancies. The conference report, published in Nature Astronomy in 2026, made clear that the field is at a turning point. This is not a minor correction to an otherwise healthy model. This could require new fundamental physics. And the crisis does not stop at early galaxies. It connects directly to the problem we discussed in Chapter 1, the Hubble tension, the expansion rate that does not match, the model that predicts one number while the universe stubbornly delivers another. These are not separate problems, they are symptoms of the same disease. The lambda CDM model, the standard model of cosmology that has governed our understanding of the universe for a quarter century, may be failing. And if it fails, everything built on it, our estimates of the age of the universe, the size of the universe, the fate of the universe, all of it comes into question. The Hubble tension is the crack in the wall, and every new measurement is making it wider. Chapter 10, the Hubble crisis. 2 numbers. That is all it takes to throw the entire field of cosmology into crisis. 2 numbers that should agree and do not. The first number comes from the cosmic microwave background, the afterglow of the Big Bang. mapped in exquisite detail by the European Space Agency Planck satellite from 2009 to 2013. Using the patterns in the CMB and the standard lambda CDM model, cosmologists calculated the expansion rate of the universe. They arrived at a value of approximately 67.5 kilometers per second per megaparsec. A megaparsec is 3.26 million light-years. So for every 3.26 million light-years of distance between 2 points in the universe, the space between them is expanding at 67.5 kilometers per second. The Atacama Cosmology Telescope, a ground-based radio telescope in the Chilean Andes, refined this measurement. Combining CMB data with observations of galaxy clustering and stellar ages, they got a value of about 68.22, slightly higher than Planck but consistent with it. The early universe route was solid, approximately 67 to 68. The second number comes from the local universe. Instead of looking at the earliest light in the cosmos and working forward with a model, astronomers measure distances and velocities directly, using the cosmic distance ladder. The distance ladder is a chain of techniques, each calibrated by the one below it. The first rung uses geometric methods, parallax, to measure distances to nearby stars. The second rung uses those nearby stars to calibrate the brightness of Cepheid variable stars, pulsating stars whose intrinsic luminosity is directly related to their pulsation period. Measure the period. Calculate the true brightness. Compare it to the observed brightness. Get the distance. The third rung uses Cepheids in distant galaxies to calibrate even more distant indicators, like Type Ia supernovae. Each rung extends the reach of the last, building a bridge from our solar neighborhood to galaxies billions of light-years away. Using this ladder, the SH0ES team, led by Nobel laureate Adam Rees of Johns Hopkins University, has consistently measured the Hubble constant at approximately 73 kilometers per second per megaparsec. Other teams using independent methods have gotten similar results. The tip of the red giant branch method, which uses a different type of star to calibrate distances, gives values in the range of 69 to 72. Surface brightness fluctuation measurements give about 73.8. And in 2025, Daniel Skolnick of Duke University published a new measurement in the Astrophysical Journal Letters that pushed the local value even higher. His team used the Coma cluster, one of the most well-studied galaxy clusters in the sky, as a calibration point. The Coma cluster is in our cosmic backyard. Its distance has been measured repeatedly by multiple independent methods over decades. Using this high-precision measurement as their first rung, combined with data from the Dark Energy Spectroscopic Instrument, they arrived at a Hubble constant of 76.5 kilometers per second per megaparsec. 67 from the early universe. 76 from the local universe. The gap is not closing, it is widening. For years, skeptics suggested that the discrepancy might be due to measurement error. Perhaps the Cepheid observations were contaminated by dust. Perhaps crowded star fields made the measurements unreliable. Perhaps the calibrations were subtly wrong. In 2024 and 2025, the SH0ES team used the James Webb Space Telescope to re-observe the same Cepheid variable stars that had anchored their measurements. James Webb infrared capabilities provided sharper, cleaner images than the Hubble Space Telescope could achieve. The result, the Hubble data was correct. The Cepheids were exactly where and how bright the earlier measurements said they were. Dust and crowding were not the problem. The local measurement of approximately 73 was robust. Then, in December 2025, the TDCOSMO collaboration published results from a completely independent method, time delay cosmography. This technique uses gravitationally lensed quasars. When a massive galaxy sits between us and a distant quasar, the galaxy gravity bends the quasar light, creating multiple images of the same object. Because each light path has a different length, the images arrive at slightly different times. By measuring these time delays and modeling the mass distribution of the lensing galaxy, astronomers can calculate the Hubble constant directly. No Cepheids, no supernovae, no distance ladder at all. Their result matched the local measurements, not the CMB value. Every new independent method that measures the expansion rate of the local universe gets the same answer. And it is the wrong answer according to lambda CDM. As of late 2025, the discrepancy has reached 5 sigma. In physics, 5 sigma is the gold standard for a real result. It is the same threshold used to claim the discovery of the Higgs boson at CERN in 2012. A 5 sigma result means the probability that the discrepancy is due to random chance is less than 1 in 3.5 million. This is not a fluke. This is not noise. This is something real. Skolnick said it directly. This is saying, to some respect, that our model of cosmology might be broken. He added, "We are at a point where we are pressing really hard against the models we have been using for 2.5 decades, and we are seeing that things are not matching up." So what could fix it? What could explain why the universe appears to be expanding faster locally than the early universe data predicts? Several ideas are on the table. Early dark energy is one of the leading proposals. The idea is that a brief burst of extra dark energy existed in the universe before recombination, before the CMB was released. This extra energy would have altered the size of the sound horizon, the characteristic scale imprinted in the CMB, which in turn would change the Hubble constant derived from that data. In effect, the CMB value would shift upward, potentially matching the local measurements. But early dark energy models struggle to fit all the CMB data simultaneously. They fix one problem and create others. New neutrino physics is another proposal. If there are more species of neutrinos than the 3 we know about, or if neutrinos have unexpected properties, this could alter the expansion history in the right direction. Modified gravity theories, which adjust Einstein general relativity at cosmological scales, have also been explored. In 2025, a team led by Karsten Jadamczyk published a paper in Nature Astronomy proposing a different culprit: primordial magnetic fields. Tiny magnetic fields that may have existed from the earliest moments of the universe. Using supercomputer simulations at Simon Fraser University, the team showed that these fields could have accelerated the process of recombination, changing the patterns in the CMB in ways that would shift the derived Hubble constant. If primordial magnetic fields existed, the CMB value of 67 might actually be an underestimate. The true value could be higher, closer to the local measurements. Levon Pogosian, a co-author and professor at Simon Fraser University, said this could address 2 major unsolved puzzles: the Hubble tension and the origin of cosmic magnetic fields. And then there is the void hypothesis, the possibility that we mentioned in Chapter 3. If the Milky Way sits near the center of the KBC void, a region of below-average density roughly 2 billion light-years across, then the local expansion rate would naturally appear higher than the cosmic average. Galaxies inside a void are pulled outward by the denser surrounding regions, amplifying the local expansion. We would not need new physics. We would just need to accept that our address in the cosmos is slightly unusual. None of these solutions has been confirmed. None has been universally accepted. The lambda CDM model, which has been the bedrock of cosmology for 25 years, has survived every challenge until now. It may still survive this one. Perhaps a combination of small effects will close the gap. Perhaps a subtle systematic error lurks in one of the measurement chains that no one has found yet. Or perhaps the model is truly breaking. Perhaps the universe is telling us something we do not yet know how to hear, that the physics we have used to build our picture of reality is incomplete. That something new, something fundamental, something we have not yet imagined, is required to understand how the universe actually works. And if our model of the universe is wrong about how fast it is expanding, it might also be wrong about how big it truly is. The observable universe, 93 billion light-years, is calculated using lambda CDM. If the model changes, the number changes. And beyond the observable universe, beyond the edge of sight, the estimates for the true size of the cosmos are not just large, they are staggering. Chapter 11. Beyond the Wall. The observable universe is 93 billion light-years across. That is a sphere containing 2 trillion galaxies, 10 to the power of 24 stars, and more planets than we can count. It is everything we have ever seen, everything we have ever measured, everything that light has had time to deliver to our instruments since the universe was born. It is a fraction, a tiny, almost insignificant fraction of what actually exists. We know this because of one measurement, one deceptively simple property of the universe that has been confirmed to extraordinary precision. The universe is flat. In cosmology, flatness does not mean the universe is shaped like a table. It refers to the geometry of space itself. In a flat universe, the angles of a triangle add up to 180 degrees. Parallel lines stay parallel forever. Space does not curve back on itself. In a positively curved universe, like the surface of a sphere, the angles of a triangle add up to more than 180 degrees, and parallel lines eventually converge. The universe would be finite but unbounded. Like a balloon, you could travel in a straight line and eventually return to where you started. In a negatively curved universe, like the surface of a saddle, the angles add up to less than 180 degrees, and parallel lines diverge. Measurements from the cosmic microwave background and from baryon acoustic oscillations, the fossilized sound waves from the early universe imprinted on the distribution of galaxies, tell us that the universe is flat to within 0.4%, 99.6% flat. The curvature, if it exists at all, is so slight that within the entire observable universe, space is indistinguishable from perfectly flat. And this has a staggering implication. If the universe was strongly curved, it could be small. A positively curved universe, like the surface of a sphere, could be finite and not much larger than the observable volume. But the flatter the universe is, the larger it must be. Because the only way for our 93 billion light-year observable patch to appear perfectly flat is if the total universe is vastly, overwhelmingly larger. The same way a basketball court appears flat to an ant, but only because the curvature of the Earth is too gradual to detect at that scale. A team of researchers at Oxford University analyzed the curvature constraints from the CMB and concluded that the universe is at least 250 times larger than the observable portion. At minimum, the full universe would be at least 23 trillion light-years in diameter. Its volume would be over 15 million times what we can see. Let that settle. Everything we have discussed in this documentary, every galaxy, every void, every filament of the cosmic web, every supercluster, every measurement ever made by every telescope ever built, all of it fits inside a volume that is, at best, 1/15 millionth of the whole. And that is the conservative estimate. Alan Guth, the physicist who proposed the theory of cosmic inflation in 1980, has estimated the size of the universe based on inflationary models. His numbers are not gentle. Cosmic inflation is the theory that in the first fraction of a second after the Big Bang, the universe underwent a period of exponentially rapid expansion. In an inconceivably brief moment, the universe expanded by a factor of at least 10 to the power of 26. A region smaller than a proton, ballooned to a size larger than the observable universe today. This inflationary burst smoothed out the universe, flattened its geometry, and set the stage for the structures we see today. If inflation happened, and the evidence strongly suggests it did, then the total universe is not just 250 times larger than the observable portion. It could be 10 to the power of 23 times larger. That is, a 1 followed by 23 zeros. 100 sextillion times the observable universe. To make that number feel like something, consider this analogy. If the observable universe were shrunk to the size of a €1 coin, the full universe, under Guth estimate, would be a sphere 250,000 light-years in diameter. That is more than twice the diameter of the Milky Way galaxy. The observable universe, 93 billion light-years across, containing 2 trillion galaxies, would be a coin, and the full universe would be larger than the galaxy we live in. And that is just one model. Some inflationary scenarios suggest the universe is literally infinite, not just very large, not just incomprehensibly large, actually infinite, extending forever in every direction, with no boundary, no edge, no center. If the universe is infinite, then every possible arrangement of matter, every possible configuration of atoms, every possible history occurs somewhere. There would be other regions of space so far away that light from them will never reach us, where the atoms have arranged themselves into an exact copy of the Earth, with an exact copy of you listening to an exact copy of this sentence, not as metaphor, as mathematical certainty. In an infinite universe with finite possible configurations of matter, repetition is not just possible, it is guaranteed. That thought is either exhilarating or vertigo-inducing, depending on your temperament. But regardless of whether the universe is 250 times larger, or 10 to the 23 times larger, or infinite, one fact is clear: we will never see most of it. The cosmic event horizon seals us in. The accelerating expansion of space ensures that the vast majority of the universe is, and always will be, beyond our reach. Light from those distant regions will never arrive. Signals from any civilization that might exist there will never be received. We are isolated, confined to our observable bubble, a tiny, luminous fishbowl floating in an ocean of unknowable immensity. Over time, our view will expand slightly. The future visibility limit extends to objects currently about 61 billion light-years away. This will roughly double the volume we can see. But even that doubled volume is a rounding error compared to the whole. We will see twice as much and still see almost nothing. The universe is not just bigger than we thought, it is bigger than we can think. It exceeds not just our instruments, but our capacity for comprehension. Our brains evolved to navigate African savannas, to track prey across distances of a few kilometers, to remember the locations of water and shelter. We did not evolve to grasp 10 to the 23. We did not evolve to feel what infinity means. We can write the equations, we can calculate the estimates, but we cannot experience the scale. And yet the equations point somewhere. The models, the mathematics, the logical extension of inflation, all point toward the same unsettling conclusion. If inflation happened once, it probably did not happen just once. The same physics that inflated our universe may be inflating others. Right now, in regions of space so far beyond our horizon that the word distance loses its meaning, the universe we see may not be the universe. It may be a universe. One bubble in an infinite sea of bubbles, each with its own Big Bang, its own expansion, its own physics, its own stars and galaxies and voids, and maybe, just maybe, its own observers, looking up at their own night sky and wondering if they are alone. Chapter 12. The Multiverse. If cosmic inflation happened, and the evidence from the cosmic microwave background, the flatness of space, and the uniformity of the universe on large scales all suggest it did, then most models of inflation predict something extraordinary. They predict that inflation does not stop everywhere at once. Inflation is not a one-time event, it is a process, a runaway expansion of space driven by the energy of a quantum field. In our region of space, inflation eventually ended. The energy of the inflaton field decayed, the expansion slowed, matter formed, galaxies emerged, stars ignited, life arose. But in other regions of space, farther away than any photon could ever travel, inflation may still be going. Right now, the quantum field that drove the expansion in our neighborhood may still be driving expansion in others. This idea was formalized in the early 1980s by physicists including Paul Steinhardt and Alexander Vilenkin, and further developed by Alan Guth. They called it eternal inflation. In this framework, our Big Bang was not the beginning of everything. It was a local event, one pocket of space where inflation happened to stop, where the energy of the inflaton field happened to decay, where conditions happened to be right for particles and forces and eventually galaxies and planets and life. But outside our pocket, inflation continues, and it continues forever, because inflation is exponential. The inflating regions of space expand faster than the pockets where inflation ends. Even as bubble universes like ours form and begin their own slow expansion, the space between them inflates faster, creating room for more bubbles, more pocket universes, each with its own Big Bang, its own initial conditions, its own history. The result is a multiverse, not in the science fiction sense, not parallel dimensions accessed through portals or mirrors, a multiverse in the most literal physical sense. An infinite collection of causally disconnected pocket universes, each one expanding and evolving independently, each one inaccessible to every other. No signal can pass between them, no light, no gravity, no information of any kind. They are islands in an ever-expanding sea of inflating space. And here is where it gets truly strange. In some versions of the multiverse, particularly those derived from string theory, the physical constants that govern our universe are not fundamental, they are contingent. String theory, the leading candidate for a unified theory of physics, predicts an enormous number of possible vacuum states. Each vacuum state corresponds to a different set of physical laws, different strengths of gravity, different masses for particles, different numbers of spatial dimensions. The total number of possible configurations is estimated at 10 to the power of 500, a number so large that writing it out would require more digits than there are atoms in the observable universe. In the string landscape version of the multiverse, each bubble universe could settle into a different vacuum state, a different set of physical laws. Some universes might have a strong nuclear force so weak that atoms cannot form. Some might have a cosmological constant so large that space tears itself apart before galaxies can coalesce. Some might have no stable matter at all, just a formless sea of radiation expanding into nothing. Others might have conditions similar to ours, with stars and planets and the potential for chemistry and complexity and life. The laws of physics we observe, the specific values of the gravitational constant, the speed of light, the mass of the electron, the strength of electromagnetism, may not be the laws of the universe. They may be the laws of our universe. Local conditions, one roll of an infinite cosmic dice. And we exist in this particular role not because it is special, but because it is the kind of role that allows observers to exist at all. This reasoning is called the anthropic principle. We see the universe we see because it is the kind of universe that produces beings capable of seeing. Whether the multiverse is a prediction, a philosophical proposition, or something in between is one of the most contentious questions in modern physics. Critics argue that a theory which predicts everything predicts nothing. If any set of physical laws is possible in some pocket universe, then nothing is falsifiable. The multiverse becomes a framework that can explain any observation by pointing to a different bubble where that observation would occur. This, critics say, is not science, it is metaphysics. Proponents push back. They argue that eternal inflation is not a speculative add-on to physics. It is a natural, almost unavoidable consequence of the same inflationary theory that has been confirmed by CMB observations. If you accept inflation, and most cosmologists do, then eternal inflation follows from the mathematics. You do not get to keep the part of the theory you like and discard the part that makes you uncomfortable. And there are hints, faint, tantalizing, far from conclusive, that the multiverse might leave fingerprints. If two bubble universes happen to nucleate close enough in the inflating space, they could collide. A bubble collision would leave a specific pattern in the CMB, a circular bruise of slightly different temperature in the microwave background. Some researchers have claimed to find anomalous features in the CMB data that could be consistent with a bubble collision. Cold spots, asymmetries, patterns that do not fit the simplest lambda CDM predictions. These claims are highly debated. The statistical significance is below threshold, but they exist. They sit at the edge of the data like shadows at the periphery of vision. In 2018, shortly before his death, Stephen Hawking co-authored a paper with Thomas Hertog proposing a way to reduce the multiverse from an infinite ensemble to something finite and potentially testable. Using the holographic principle, a concept from string theory that suggests the physics of a volume of space can be described by a theory on its boundary. Hawking and Hertog argued that eternal inflation could be described by a finite set of possible histories. This would make the multiverse, in principle, subject to observational constraints. Gravitational wave astronomy, they suggested, might eventually provide the data needed to test these ideas. The multiverse remains at the boundary of science and philosophy. It is the most extreme logical extension of the physics we trust. It cannot be confirmed by any observation currently conceivable, but it cannot be ruled out either. It is the ultimate expression of the theme that has run through this entire documentary. The universe is larger than we thought, not just larger in a way that defies intuition, experience, and in some formulations the very concept of size. If the multiverse is real, our universe is one island in an infinite archipelago. Each island has its own ocean, its own weather, its own geology. Some are habitable, most are not. We are on one of the habitable ones, marveling at the sky and wondering whether the ocean has a far shore. It may not. The ocean may be infinite. But even within our single island, within our one observable universe, within this 93 billion light-year bubble of light and matter and dark energy, the question that haunts us most is not about physics. It is not about expansion rates or vacuum states or bubble collisions. It is simpler than that, more ancient than that. It is the question every civilization has eventually asked. In all of this vastness, in all of these trillions of galaxies and billions of trillions of stars and countless planets in countless habitable zones, is there anyone else? Is anything out there looking back? Or are we alone? Completely, utterly, cosmically alone, staring into the dark, waiting for an answer that never comes. Chapter 13. Are we alone? Let us talk about the numbers, because the numbers are overwhelming. The observable universe contains roughly 2 trillion galaxies. Each galaxy contains on average 100 billion to 400 billion stars. The total number of stars in the observable universe is estimated at 10 to the power of 24, 1 septillion, a 1 followed by 24 zeros. Most of those stars have planets. Data from the Kepler Space Telescope and ground-based surveys suggest that the average star in the Milky Way hosts at least one planet. Many stars host multiple planets. Current estimates suggest there may be more planets than stars in our galaxy alone. In the Milky Way, conservative estimates place the number of rocky planets in the habitable zone, the orbital range where liquid water could exist on a planet's surface, at between 300 million and 10 billion. Scale that up. If there are 300 million habitable zone rocky planets in the Milky Way and 2 trillion galaxies in the observable universe, the total number of potentially habitable worlds is in the billions of trillions. And if the universe is 250 times larger than the observable portion, or 10 to the 23 times larger, or infinite, then the number of potentially habitable worlds is beyond any meaningful estimate. The probability that Earth is the only planet in all of that where life arose is not just small, it is absurd. unless there is something about life we fundamentally do not understand, unless the leap from chemistry to biology is so improbable that even with billions of trillions of chances, it has happened only once. We do not know the probability of abiogenesis, the emergence of life from non-living chemistry. It could be common, it could be vanishingly rare. We have a sample size of 1, Earth, and from that single data point, we cannot draw conclusions. Life could be everywhere, or we could be alone. Both are consistent with the evidence. But if life is not rare, then the silence is deafening. In 1950, the physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory. The conversation turned to the question of extraterrestrial life. Fermi, known for his ability to make quick back-of-the-envelope calculations, considered the age of the galaxy, the number of stars, the likelihood of planets, and the time it would take a technologically capable civilization to colonize the galaxy even at modest speeds. His conclusion was simple and devastating. If intelligent life is common, the galaxy should be teeming with it by now. Civilizations have had billions of years to spread. Even at speeds far below the speed of light, a single civilization could colonize the entire Milky Way in a few tens of millions of years. A blink in cosmic time. And yet there is no evidence that anyone has done so. No confirmed signal, no visitation, no artifact, no megastructure visible in our telescopes. Nothing. Where is everybody? That question became known as the Fermi paradox. And in the decades since Fermi asked it, the paradox has only deepened. Our telescopes have grown more powerful. Our surveys have expanded. We have listened for radio signals with projects like the Search for Extraterrestrial Intelligence, SETI. We have scanned the skies for laser pulses, infrared signatures, and other techno-signatures. We have found nothing. The explanations for the silence are numerous, and each one is unsettling in its own way. The Great Filter hypothesis suggests that somewhere between dead chemistry and a galaxy-spanning civilization, there is a barrier, a step so difficult that almost no one gets past it. The question is whether the filter is behind us or ahead of us. If the filter is behind us, if the hard step was the origin of life, or the development of complex cells, or the evolution of intelligence, then we are among the lucky few who made it through, and the universe is full of microbial worlds that never took the next step. If the filter is ahead of us, if civilizations commonly arise but invariably destroy themselves through war, or environmental collapse, or technological catastrophe before becoming interstellar, then our future is grim. The zoo hypothesis proposes that advanced civilizations exist but deliberately avoid contact with us. They are watching but not interfering. The dark forest theory, popularized by the science fiction author Liu Cixin, suggests that advanced civilizations stay silent because the universe is dangerous. Any civilization that reveals itself risks destruction by others. The safest strategy is to remain hidden, to treat the cosmos as a dark forest in which every rustling bush might be a predator. And then there is the simplest explanation of all: distance. Everything we have discussed in this documentary has been building toward this realization. The universe is not just big, it is structured to isolate. The cosmic web separates galaxies along filaments spanning hundreds of millions of light years. The voids between the filaments are chasms of emptiness. The expansion of space is accelerating, pushing galaxy clusters apart faster and faster. The cosmic event horizon seals off most of the universe permanently. Even within the Milky Way, the distances are paralyzing. The nearest star is 4.24 light-years away. At Voyager 1 speed, 73,000 years away. A radio signal sent today would take 4 years to arrive. A response would take another 4, and Proxima Centauri is the nearest star. The galaxy is 100,000 light-years across. A signal sent from one side to the other would take 100,000 years to arrive. civilizations could rise and fall in the time it takes their first message to reach the far side of the galaxy. And our radio signals, our electromagnetic calling card, our only evidence that we exist, have traveled just 125 light-years. A sphere 125 light-years in radius inside a galaxy, 100,000 light-years wide. It is a whisper in a cathedral. And beyond the Milky Way, the distances become so absurd that the question shifts from, will we find anyone, to, could we ever know if anyone is there? The Andromeda Galaxy is 2.5 million light-years away. The nearest large galaxy cluster, the Virgo cluster, is 54 million light-years away. A message sent there today would arrive 54 million years from now. The sender species would likely be long extinct before the response came back. Communication across the cosmic web is not merely difficult, it is functionally impossible on any timescale relevant to a biological civilization. This may be the answer to the Fermi paradox. Not that intelligent life is rare, not that civilizations destroy themselves, not that they are hiding, but that the universe is too large. The distances are too great. The cosmic architecture itself is a quarantine. Every civilization is an island, surrounded by an ocean of space so vast that no message, no ship, no signal can bridge it in any meaningful sense. We are not alone because life is impossible elsewhere. We are alone because togetherness is impossible across these distances. The universe may be full of voices, all of them calling out, all of them unheard. The question is not just, are we alone? The question is, could we ever know? And maybe, in the end, the answer is no. Maybe the universe is built in such a way that its inhabitants are forever isolated, forever wondering, forever staring at the same stars and asking the same question and never receiving an answer. Maybe the silence is not a mystery to be solved. Maybe it is a feature, a fundamental property of a cosmos too large for any of its children to find each other. That is a lonely thought, but it is not the last thought, because there is another way to look at this, another way to interpret our smallness, our silence, our isolation, a way that does not end in despair, a way that ends in something like wonder. Chapter 14. The Pale Blue Dot Revisited. On February 14, 1990, the Voyager 1 spacecraft was 6 billion kilometers from Earth. It had finished its planetary mission. The cameras were about to be shut down permanently. Carl Sagan, the astronomer and author who had championed the Voyager program from the beginning, made a request to NASA: turn the camera around, take one last photograph, not of a planet, not of a moon, of home. NASA agreed. Voyager 1 rotated its camera and pointed it back toward the inner solar system. The resulting image showed Earth as a tiny speck, a pale blue dot, less than a pixel wide, caught in a scattered beam of sunlight, barely visible against the vastness of space. Sagan looked at that image and wrote words that have echoed through the decades since. He described how everything we have ever known, every human being who ever lived, every king and peasant, every saint and sinner, every young couple in love, every mother and father, every inventor and explorer, every teacher of morals, every politician, every superstar, every leader, every hero and coward lived out their lives on that mote of dust suspended in a sunbeam. That photograph was taken from 6 billion kilometers, barely outside the solar system, a distance that, in cosmic terms, is nothing. It is not even a rounding error. It is not even the first step on the staircase that leads to interstellar space, let alone to the edge of the galaxy, let alone to the edge of the observable universe. And already, from that trivial distance, Earth was invisible. Now consider what we have learned tonight. The observable universe is 93 billion light-years across. The Milky Way, our galaxy, is 100,000 light-years across and contains 250 billion stars. Earth orbits one of those stars, an unremarkable yellow dwarf in a minor spiral arm. Our radio signals have traveled 125 light-years, a tiny bubble in a galaxy that does not know we are here. The Milky Way is one of 100 galaxies in the local group. The local group is a speck within the Virgo supercluster. The Virgo supercluster is a lobe of Laniakea. Laniakea is one structure on the Pisces-Cetus supercluster complex, and that filament is roughly 1% of the observable universe. The observable universe itself may be 1/15 of the full universe, or less, or infinitely less. It may be one bubble in an infinite multiverse, each bubble with its own physics, its own stars, its own empty voids. We are nothing. By every measure of size, scale, distance, and time, we are nothing. A virus on a grain of sand in a desert that stretches forever. And yet we are here, and we know all of this. That is the paradox. That is the miracle, if you want to call it that. The universe is 13.8 billion years old. For most of that time, it was a hot fog, then a cooling darkness, then a slow gathering of matter into stars and galaxies and planets. For billions of years, there was no one to see it. The cosmic web wove itself in silence. The voids expanded without witnesses. The filaments glowed, and no one observed the glow. Then, on one small rocky planet, orbiting one small star on one thin filament of the web, something happened. Atoms that had been forged in the cores of stars, scattered by supernova explosions, gathered by gravity, organized by chemistry, crossed a threshold. They became aware. They looked up. They asked questions. Every atom in your body was made in a star. The iron in your blood was forged in a supernova. The calcium in your bones was assembled in the last moments of a dying star, more massive than the sun. The hydrogen in the water that fills your cells has been around since the first minutes after the Big Bang. You are not separate from the universe. You are the universe. A specific arrangement of the universe matter that has developed the capacity to contemplate itself. Hydrogen, given 13.8 billion years, became a thing that could wonder about hydrogen. That is not insignificance. That is the most extraordinary thing that has ever happened. The universe did not just produce matter. It did not just produce stars. It did not just produce galaxies. It produced observers, beings capable of measuring 93 billion light-years of reality from a planet 12,742 kilometers in diameter, beings capable of detecting the afterglow of the Big Bang, of photographing a single strand of the cosmic web, 3 million light-years long, of identifying a galaxy 280 million years after the beginning of time, of calculating that 95% of reality is made of things they cannot see. We are small, impossibly small, but we are the part of the universe that knows how small it is, and that knowing is not nothing. That knowing is extraordinary. Carl Sagan understood this. His pale blue dot speech was not a lament. It was a call. He was not saying we are meaningless because we are small. He was saying our smallness demands that we treat this place, this moment, this speck with care, because it is all we have, because there is no evidence that anyone else is coming to save us. Because the vastness of the cosmos does not make our lives less precious, it makes them more precious, concentrated, rare, possibly unique. The universe is under no obligation to make sense to you. It is under no obligation to be the size you would prefer. It is under no obligation to contain neighbors you can visit or signals you can detect. It simply is. Vast, mostly empty, mostly dark, mostly unknown. But you exist anyway, against overwhelming odds, against the indifference of entropy and the emptiness of the voids and the silence of the sky. You exist on a filament of the cosmic web, in a void within a void, circling a star that will someday die, on a planet that will someday be swallowed by that dying star, in a galaxy that will someday merge with Andromeda, in a universe that is slowly going dark. And right now, in this brief moment, in this narrow window of cosmic history where the CMB is still detectable and the distant galaxies are still visible and the story of the universe can still be pieced together, you are here, listening, thinking, wondering. The universe has been around for 13.8 billion years. Human civilization has existed for roughly 5,000. You have been alive for a handful of decades. The window during which you exist, the sliver of time during which your atoms are arranged in a way that can experience and contemplate and feel, is so thin that it should not register on any cosmic scale. And yet it does, because you are the universe way of experiencing itself. You are not a bystander, you are the cosmos, briefly aware. Every measurement we discussed tonight, every number, every light year, every billion, was calculated by beings made of stardust using instruments built on a pale blue dot. That is not a footnote to the story of the universe. That is the climax. That is the point. The universe spent 13.8 billion years building something that could look at it and say, I see you, I measure you, I understand you, and I am so very, very small. Maybe that is the point. Maybe the universe does not need to be understood by something large. Maybe understanding is its own scale. Maybe consciousness, awareness, the simple act of looking up and feeling awe, is the largest thing in the cosmos. Not in meters, not in light years, in meaning. The Boots void is 330 million light years of almost nothing, but it has never known it is empty. You know, the cosmic web stretches across the entire observable universe, but it has never seen itself. You have. The multiverse, if it exists, contains infinite possibilities, but none of them matter unless something, somewhere, is aware of them. You are that awareness. Fragile, temporary, impossibly rare, but real. The universe is not empty. It just feels that way because we are small, and space is vast, and the light takes so long to travel. But somewhere, on a thin filament of the cosmic web, in a void called the local hole, circling an ordinary star, on a planet that still has blue oceans and green forests, and people who look up at the night sky and wonder, the universe is looking at itself and wondering what it means. If you enjoyed this deep exploration of the cosmos and what it means to be part of it, please like this video and subscribe to the channel. Tell us in the comments what surprised you most about the true scale of the universe and what should we explore next. These are not just questions for scientists, they are questions for all of us. Because the universe is not something out there. It is something we are part of, and every question we ask about it is a question we are asking about ourselves. Thank you for spending this time with us. We will see you in the next journey.